Hello, students. Welcome back. Today we're going to be doing multivariable linear system, Gaussian elimination, and row-echelon form. So last time we learned about the two variables equations, the system of linear equations, and system of nonlinear. So today we're going to be increasing our system of linear equations by one more variable. So let's take a look at this equation. So it's 1.1. So we're going to have x minus 2y plus 3z is equal to 9, right? So we added one more variable. Then we're going to have negative x plus 3y is equal to negative 4, and then 2x minus 5y plus 5z is equal to 17, right? So this is a system of three equations. We have three equations, and we have three unknowns. So perfect. That means we try to find a solution to this equation. And first thing that we're going to be learning today is the row-echelon form. So row-echelon form, that formula of equation is essentially means a stair-step pattern with leading coefficient of 1. So leading coefficient, so each row corresponds to the variable that we want to find. So the way it goes, so the first row is the x variable. Second row is the y variable. Last row. So the way we have to find it is the z going to be the last one. The first one, then y, then x. Okay. And so if we want to write it in the row-echelon form, we would have to do the elimination such that at the end, we're going to end up with this kind of equation. So our first equation is x minus 2y plus 3 is equal to 9. So nothing really there. Second equation became y plus 3z is equal to 5. Meanwhile, z became just z equal to 2. So when I said about the leading coefficient is the number right in front of the row variable that we want to find. So here is 1 times x, 1 times y, 1 times z, right? Before we had 5, 3, and here we had 1, but we reduced it such that now it's just 1, 1, 1. So when we solve it, it's a simple substitution, and we got x, y, and z. Okay, so here it is easy to substitute, right? Because if we substitute back, so backwards, right, third case, we have that z is equal to 2, then y plus 6 is equal to 5, so y is equal to negative 1. And x, so we're going to have x minus, going to be plus 2, plus 6, so goes to 9, so 9 minus 6, that's 3, minus 2, that's 1, so x is 1. So our solution is actually 1, negative 1, 2. Right, so it's a three-dimensional solution, so that would be a point on a plane. Okay? So each equation, 1, 2, and 3, essentially represents some sort of a plane, because now we are in 3 dimensions. Okay, and why do we need a row-echelon form? We need the row-echelon form to be able to perform Gaussian elimination. Okay? So let's go ahead and actually introduce Gaussian elimination, because we will be applying the row-echelon form towards the Gaussian elimination. So each of the following row operations on the system of linear equations produces equivalent system equations. So what can we do when we have two equations? We can interchange the two equations. We can multiply one equation by a non-zero constant. We have to multiply both sides, left and right. And then we need to add or multiply of one equation to another equation to replace the later equation, right? So essentially, if we have equation 1 and 2, I can multiply the equation 1 by a number, then add it to the equation 2, and change equation 2. Right, so we're going to do that on the example. So our second example is going to be following. So we're going to have a simple system of equations. So 3x minus 2y is equal to negative 1. X minus y is equal to 0. So I'm going to call it R1 and R2. Okay, so what I want to do is I want to see if I can get rid of something. So let's take a look and try to get rid of x, for example. Right, I don't like x, I want to get rid of it. So what I'm going to do is I'm going to say, well, I'm going to multiply row 2 by negative 3. right? So -3 times row 2 plus row 1. So I'm going to add it to row 1, and I'm going to change row 1. This means change, right? Right here, change row 1. So I'm not going to change row 2. So, okay. So I'm still have x minus y being equal to 0. But now, and of course I can move that equation upwards. Actually, that's what I'm going to do. I'm going to have x minus y is equal to 0. Meanwhile, the second equation, right, because I multiplied by -3, so when we multiplied by -3, it became -3x plus 3y equal to 0. Right? And I wanted to add the first equation, so I'm adding it to the first equation. So I'm going to have 0x plus y is equal to -1. So, okay, y is equal to -1, right? And we have x minus y equal to 0. Y is equal to -1. So we have a row echelon form here, right? A staircase. So now I can just plug in y into the first equation. X minus negative equal to 0. Y is equal to 1. And we get that x is equal to -1. And y is equal to 1. So our solution is -1, -1. Okay. Right, so essentially, now we used it as rows. And well, even though for the two variables, right, two equations, it's not really convenient to use such method. It's much more efficient and much more convenient when we have a system of 3 equations, right? And what we're trying to do is we would be trying to add the equations together, and for especially for 3 variables, and trying to eliminate it such that we would get the row echelon form. Okay, so let's take a look at our initial example that I gave at the beginning. So, but now we're going to be applying these techniques, and we actually name it row 1, 3, and actually solve it this way and bring it to the row echelon. So, example 1.3. Okay, so we have x minus 2y plus 3z is equal to 9, minus x plus 3y is equal to -4, and 2x minus 5y plus 5z is equal to 17. Right, very similar equations. So let's take a look at, well, it's the same one. But let's take a look at how can we do it. So of course I'm going to name it first each row, right? So I'm going to call this one to be row 1, row 2, row 3. I'm going to interchange them as we go. I'm going to do operations to them. So the very first thing I want to do for this equation is let's go ahead and add equation 1 to equation 2 and change equation 2. So I'm going to have row 1 plus row 2 change row 2. The reason why I want to change it is because of this. Right, we can get rid of x, and that's it's convenient for us, right? Because we know that the second row will be only in terms of y and z, right? Because we're getting rid of anything that bothered it, because we know this is going to be x row, this is going to be y row, this is going to be z row. So in z row we can only have z. In y row we can have yz. In x row we can have xyz. Okay, so if we do so, we're going to have x minus 2y plus 3z is equal to 9. When we add the two equations, what are we going to have here? We're going to have y plus, we will have 3z is equal to 5. And then the last one is going to be 2x minus 5y plus 5z is equal to 17. Okay, so that's our row 1, row 2, row 3, right? That's now our row 1, row 2, row 3. Okay, now we once again going to perform some of the operations. Okay, what we want to do is we want to multiply the first equation by -2 and add it to the third equation. So, and change the third equation. So we're going to have -2 times r1 plus r3 change r3, right? Because we're keeping r1 the same. Don't really need to change anything. It's already in the row echelon form essentially because it has 1x in front of it. We don't have to do anything, right, to change it. So what are we going to have here? We're going to have still x minus 2y plus 3z 9. The second row remains the same, right? So we're going to have y plus 3z 5. Meanwhile, what's going on here? So we're going to have negative 2x plus 4y minus 6z is equal to negative 18. We're adding it to 2x minus 5y plus 5z is equal to 17. Okay, so if we add that, we're going to get 0x, right? Minus y minus z negative. Okay, so we get negative y, negative z equal to negative 1. Okay, and now, again, this is our row 1, row 2, row 3. Okay, so now let's take a look. What can we do here? Let's go ahead and add row 2 plus row 3, and we're going to change once again row 3, right? Because row 2 is already in the row echelon form. So we're going to get that first row becomes still remains x minus 2y plus 3z is equal to 9. Second row still remains y plus 3z is equal to 5. Meanwhile, the third row, so we were adding it, y plus y, that's 0, y goes away. 3z plus negative z, that's going to be 2z, is equal to 5 plus negative 1, that is 4. Okay, and then our last step here is to actually, we're going to have 1/2 times row 3, change row 3, so we're going to divide row 3 by 2, so we get rid of the coefficient 2 in front of the z. Right, and so our row echelon form of the equation that I showed you in the beginning is going to be x minus 2y plus 3z is equal to 9, y plus 3z is equal to 5, z is equal to 2. And once again, if we solve the equation, we can plug it back in, and we're going to have that we have 1 comma negative 1, 2 as our solution. So this way, the systematic way, is very, very useful to have in algebra, essentially, right? The system of equations. So sometimes it's going to be much more difficult to do substitutions or to do some sort of eliminations most of the time. So keeping track of row and doing the row echelon for either way of doing it, and it will lead to later on. Once we learn matrices, we're going to be able to write it down in matrices faster than we are currently doing right now. But first, we have to learn the basics of the elimination, Gaussian elimination. So now let's take a look at some of the possibilities, right? Some of the possibilities of the equation. So we might have a solution, right? We might have a solution for one point or one line or non-solutions, right? So since we're talking about 3 dimensions, right, we're not talking about lines anymore. We're talking about planes, right? So essentially, when we have system of 3 variables, so we have 3 equations, in 3-dimensional space, it will actually be written as this, right? We have equation 1, so I can label it as, R1, R2, and R3, right? So essentially, that's 3 different planes, and if we do have solution, just like in the previous case, those planes are going to be intersecting this way. Now, if we have a solution as one line, because sometimes we might have solution as in terms of z, let's say, right? Then that means there's going to be a line that's going to be intersecting, right? And that's going to be our solution, as we're going to be able to eliminate z, but we're not going to be able to eliminate x and y. Then a solution in plane, right, when we're not able to eliminate much, right? And now we have still 3 variables, but only as a one equation. And if we don't have any solution, the line's just not going to be intersecting at the single point, right? So here's an example. Yep, actually, this one has no solution. This one does not have any solution. So that means, well, because R1, R2, and R3 do not intersect anywhere, right? So R1, R2, R3. So R1 and R3, we have a line, essentially, solution. Meanwhile, R2 is just not there, right? It has a solution with this R1, it has solution R2, but not a common solution between the two. So this is non-solutions. And of course, there is no solutions is if all of the three planes are parallel. Right? So we can imagine 3 parallel planes. Right? And so once again, there is none of the solutions here because all 3 are parallel. There is not a single intersection. Okay, so for a system of linear equations, the following things are always true. Right? So either 1, there's exactly 1 solution. 2, there are infinitely many solutions, as for example, the plane is the solution, or a line is a solution, right? Where we weren't able to actually simplify one of the variables. So we had to express one variable in terms of the other, and that's going to remain as the solution. So it's going to be solutions. And the third case is, of course, there are no solutions. Okay, and so when we do not have, when do we have infinite many solutions? Is when we are dealing with non-square systems, right? So non-square systems of linear equations. Systems. So essentially, right, what would be an example? Something like this. So example 2. So we would have x minus 2y plus z equal to 2, and then 2x minus y minus z is equal to 1. Remember, I said that we have a solution. We might have a solution if we have number of equations equal to number of unknowns. So in this case, we have 3 unknowns, but 2 equations. So that means, since we have 3 unknowns, that's going to be a 3-dimensional equation. So that means if we only have 2 equations, we're going to be dealing with a line, right? So we're going to have a parameter, right? A final parameter. So in this case, if let's say we simplify this equation, right? We can multiply, so R1 and R2. So we can have -2 times R1 plus R2, change R2, and then we're going to have 1/3 times R2, change R2, right? I immediately do 2 operations at once, right? Because I know what's going to be coming ahead of me. So x minus 2y plus z is equal to 2. So if we added the 2 equations, we're going to end up with so 3y minus 3z, right? 3y minus 3z is equal to -3. So that's why already beforehand I multiplied by 1/3. So it actually transforms into y minus z is equal to -1. Okay, so let's take a look. What do we actually end up with? We ended up with x minus 2y plus z is equal to 2. Okay, and we have y to be equal to so z minus 1. So actually our solution is fine here, right? So essentially because we have a parameter here, so now we have infinitely many solutions, right? Because, well, we weren't able to solve for anything. We cannot simplify z. So in this case, we can say let z to be t, which is a parameter. And by parameter, I mean that we are the ones in control of what solution we're going to have, right? So if I plug in 1, it's going to be y equal to 0. Then z is equal to 1, y is equal to 0, so x is going to be equal to 1. Right, so we got a solution, right? And now there's going to be infinitely many points of solutions because z, which is a parameter, which is equal to t now, became essentially the family of solutions, right? And of course, when we do bigger systems and we have more variables, that is a very common thing happening. And sometimes we are the ones who have to be controlling it. Okay, now let's go ahead and actually solve one of the useful applications. So, and how we can actually use the equations. So let's take a look at this problem right now. So we're going to talk about the vertical motion. The vertical motion of, let's say, a ball, or just an object in general. Okay, so here we have. So the height at times t of an object that is moving vertical, in a vertical line with a constant acceleration, is given by the position equation. The position equation is provided to us, right? And here's going to be a picture of how it looks like. So s is equal to 1/2 a, which is a is acceleration, t squared plus v naught t. V naught is the initial velocity, plus s naught, which is our position. So where s is the height in feet, a is acceleration in feet per second squared, and t is the time in seconds. V naught is the initial velocity at time naught, right? With t equal to 0. So at the very, very beginning, as the object got tossed upwards. So s sub naught is the initial height in feet, find the values a, v naught, and s naught when s is equal to 52 at time equal to 1, s equal to 52 at time equal to 2, and s equal to 20 at time equal to 3. And let's interpret the results. Okay, so how can we do that? So essentially, we're going to write down everything that we have. So when t is equal to 1, what do we got? We got 1/2 a times 1 squared plus v naught times 1 plus s naught is equal to 52. 52. Okay, when t is equal to 2 seconds, we're going to have 1/2 a times 2 squared plus v naught times 2 plus s naught is also equal to 52. When t is equal to 3, we're going to have 1/2 a times 3 squared plus v naught times 3 plus s naught is equal to 20. Okay, so now we can make a system of equations. We're going to have a plus 2v naught plus 2s naught is equal to 104. All right, we can simplify that by multiplying by 2. Then we're going to have 2a plus 2v naught plus s naught is equal to 52. Right, we just had to simplify. And then we're going to have 9a plus 6v naught plus 2s naught is equal to 40. So now we have a system of 3 equations and 3 unknowns. So can we solve it? Yes, we can. So this is actually s naught of 5. Okay, so let's go ahead and actually start. So we have row 1, or equation 1, equation 2, and equation 3. So let's go ahead and we're going to have -2 times row 1, or row or equation. This is essentially row 1, row 2, row 3, or equation 1, equation 2, equation 3. So -2 times equation 1 plus equation 2, change equation 2. Right, because once again, our first equation is already in row echelon form because we have a coefficient of 1 times a in the first equation. So that's perfect. So we're keeping it that way. So, okay, so we're going to have a plus 2v naught plus 2s naught is equal to 104. But now what are we going to have here? We're going to have, we're going to get -2v naught minus 3s naught is equal to -156. Okay, perfect. And then the third equation remains the same, so 9a plus 6v naught plus 2s naught is equal to 40. Okay, once again, now that becomes our R1, R2, 3. Okay, now let's go ahead and we're going to have the first equation multiplied by -9. So let's do a -9 times the first equation plus the third equation. Okay, and we will get to change the third equation. So again, we're going to have a plus 2v naught plus 2s naught is equal to 104. -2v naught minus 3s naught is equal to -56. And then if we add it, we're going to get -12v naught minus 60s naught is equal to -896. Now, if we multiply the second, so row 1, so our second equation, let's do it by -6 times the second equation plus the third equation, change the third equation. Okay, we will end up getting the following. So I'm going to have a plus 2 naught plus 2s naught is equal to 104. -2v naught minus 3s naught is equal to -106. And 2s naught is equal to 40. Okay, and then of course the last step is to divide the equation 2 and equation, so 1/2, so -1/2 times R2, change R2, and then 1/2 R3, change R3. All right, I'm going to do 2 at a time. So we're going to have a plus 2v naught plus 2s naught is equal to 104. Then we're going to get v naught plus 3/2 s naught is equal to 78. And s naught is equal to 20. So we immediately found the initial position, then we can find the velocity, and we can find acceleration. So we're going to have S naught is equal to 20, B naught is equal to 48, and A is going to be negative 32. Perfect. Perfect. So our final equation here, right, looking for the equation of a position, is going to be negative 16t squared plus 48t plus 20. That's going to be our position equation for essentially the graph that was provided. Right. Perfect. So next lesson, we're going to start on matrices, and we'll be able to use the matrices to simplify the Gaussian elimination and all of the processes that we've been the last couple lessons. Right, see you next lesson.